Okay, thank you very for the invitation and the opportunity to be here. So I want to discuss a bit this result that we have about the limit of Young tableaux. I will define what they are, even if I think most of you are familiar. And this is a joint work with Cédric Boutillier, Valentin Ferré, and Pierre-Louis Melliot. So I start with basic definition. I think most of you are familiar with them, just to fix notation mainly, because I take some slightly different point of view than usual. So let me recall you, an integer partition of n is just a sequence lambda 1, lambda l, which is weakly decreasing, and such that the sum of the lambda I is exactly n. And I will use this double bar around lambda to recall what is the size. So here it's a basic example. And a Young diagram is just a graphical representation of this lambda, and there are many ways of doing it. And I will do the Russian way. That is, I will plot the diagram in this 45-degree inclination. And in the first row here, I have lambda 1 boxes. So in this example, I have 6 boxes. And so I put here 6 boxes, and then 4, 4, 2, and 1. So this is what usually is called the Russian notation. And I will rescale everything in such a way that the center of each box is integer valued. And this makes the convenient fact that everything is integer valued, and the annoying fact that you have this parity condition now, that the x and y coordinate are always of different parity. So if you see some weird delta here and there, maybe it's just to fix this annoying parity condition, nothing more. Okay, this is the first remark that I needed to do. Any questions so far? Feel free to interrupt me if there is something that is not clear. And a standard Young tableau of given shape lambda is just a filling of the Russian notation of the boxes in the Russian notation with number from 1 to n, where n is the size of the diagram, in such a way that along every upwards path, you're increasing. I mean, upwards, I mean you can go up left, up right as much as you want. And everything is increasing. And you see each integer number exactly 1. There are finitely many configurations. There are available formula. Hooke formula is the best formula ever. And you can count, and there are finitely many for given n, so it makes sense to pick one uniformly at random. And I'll do that quite a lot. But the point of view that I take is a bit different than this picture. I will think of this picture as a function from lambda, where lambda is this x, y coordinate that they have this weird parity condition, into the numbers from 1 to n. Okay, so we will fix as a function where the domain is 2-dimensional and it's integer value. Okay, and I will denote always this tableau T lambda, which means it's a tableau with shape lambda. Okay, last thing, and this is probably a bit less usual, even if I know that some of you are familiar, is what is the height function of a standard Young tableau. So again, here it's the example from before. And the height function is defined like that. It's defined for every x on the real line, integer valued. And you fix a t that is the value of some box. And the height function at xt is exactly the number of boxes in the x vertical line that takes value less or equal than t. Okay, so for example, for x, I don't know, 2, we have that x2, where is 2? Is here. x2 10 is 1, because there is exactly one box that has value less or equal than 10 in this vertical ray. Okay, so here I plotted out, I fixed t, for example, t10 and t9, and I plot the function age xt for t fixed and x varying. So the bread function is 0 here. There are no boxes less or equal than 10 here and there. Then here you pick up 1 because there is this 4. Here there are 2, 3, and 9, and so on. Okay. And as you can see, the two function as a function of x, when you move t by 1, they change exactly at one place, right? So as a consequence, you can think either algebraically, and I hate to think algebraically, but if you like, it's here. I think to pick pictorially, this is a very complicated way of saying, if I give you age, you can recover t in some way. And how do you do it? You fix t equal to 9, for example, and t equal to 10. You look at where this function is changing. You go up, and it's telling you you have to put 10 in this vertical thing, and you start from going from 0 to 1, it's going to tell you where to put 1. You take the line, and you look at where the function is increasing, you put 1, and then you do for 2, and okay, this is not telling yet at what height you have to put it, but if you go from starting from 0 and going up to n, you can recursively recover the Young diagram. So in very complicated word, I just said that it's a bijection, more or less. Okay, so when I write down this formula, the only thing that I will really need is the fact that if I show you h, I can recover t, and vice versa.
So you think of this as a growing height function?
Yeah, I'll do it in a second, but that's a good point. Here we go. So we will think more in 3 dimensions in this picture, in this talk. So in the following sense, here we have a Young diagram, Young tableau, sorry, and I'll always think of it as this 3-dimensional picture. What is going on here? Okay, so you should imagine that you have this shape here in the base. Okay, so in the xy plane, you have this domain. And above each little box, you put a height function that is high as much as the value of the box. So here the function is 1, then 2, then 3, then 7, and then 10, and so on. And you see both the height in the z coordinate, but I also light it with using colors. And in the whole talk, 0 will be brownish, and then you move slowly to orange, yellow, green, and blue when you are very high. Okay, this is for how we will think about this function t. It's a 2-dimensional function in the domain, and you have the z coordinate for the value. And this is the height function. So the height function, okay, again, the colors are the same. So in particular, brown is level 0, yellowish is level 1, and the maximum that in this case is 2 is brownish. And how do you recover this function? So first of all, why the maximum is 2? Because if you fix any vertical ray, there are at most 2 boxes. So that's why the maximum is 2. But for example, what happens for 0? At 0, you are 0 until time 1. So I'm using x here and t on the y-axis. You're 0, and then when you hit 1, you pick up this box, and so you jump by 1. Then you stay constant for t up to 5. And then when you hit t time 5, you jump up again by 1 because there is a 5 here. And for example, here it happens, if you go at 1, it happens at 2, the jump, and at 9. So in other words, in every vertical coordinate, when you have a plateau, the length of the plateau is going to tell you how much you have to increase the value when you move upwards on the diagram, right? So you take this plateau, you measure the length, and it's going to tell you how much you have to add from here to there. Okay, so this is another way of interpreting exactly the bijection that I said before in a very graphical way. And I really like much more this in point of view than the crazy formula before. Any question about that?
I guess I have one.
Yeah.
Is this the same as Dan Rummick's height function for the square random tableau?
Yeah, exactly the same height function. And I will comment on that in 2 slides, probably. Okay, what is the question that I want to study is if I give you a Young diagram, how does it look like this height function and this random surface tableau when you pick one Yann diagram uniformly at random, one Yann tableau uniformly at random? So I fix the shape, pick one uniformly at random, how does it look like? I will make it more formal in a second, but I think more or less everyone understand what I mean. I want to describe this function here when they are random and when probably the size is big in some sense. But before that, why? Why do we care about that? Okay, here it's some motivation. So Yann tableaux are a dynamical version of Yann diagram. You can always think that you have a sequence of diagram that is growing just looking at the level set. The first diagram is this cube, the second diagram is this one, the third one is this one, and the fourth one is this one, and so on. And this kind of growing diagram, they have a vast literature. I will not even try to understand, to explain why and what is done, but there is a lot of research about these growing sequences. The second motivation is related to representation theory, and every person that knows a bit of representation theory knows that these Yann tableaux appear a bit here and there in many different settings. And the third motivation that is actually why I mainly care about it is because Yann tableaux are in bijection with many other interesting objects, such that permutation or sorting networks. And for example, the bijection with permutation is the famous RSK bijection, or RS bijection. And it's very nice bijection because if you want to study the length of the longest increase subsequence, it's more or less the only tool that we have. So they appear here and there. You have orthogonal motivations. We started the project mainly motivated by the last thing. But, OK, there are different settings where these objects appear. Any questions so far? OK, so let me try to formally state the problem now and to tell you what is known about this problem. OK, I need some assumptions. The first assumption is the following. Whenever I fix a Yann diagram, so just the shape, I can encode the whole shape just through this red line. If I give you the red line, now I think all of you agree that there is a unique way of recovering the shape, right? So this function, this contour function, is denoted by omega lambda for lambda a given diagram. And it's just a function from the real line into the real numbers, non-negative real numbers, which is piecewise linear, and the slope is always alternating between plus and minus 1. And the assumption that I make is the following, that we have a sequence of Yann diagrams. So again, we're just looking at the shape for the moment. Lambda n, so we have this sequence, with the following assumption. OK, the first one is not really important, that the size, the number of boxes at time n is exactly n. But actually, I just need that it's growing to infinity. And you can always relabel things in such a way that this is true. And then the more important assumption is that I'm assuming that this function, after rescaling in this direction and in that direction by a factor square root of n, it's converging to a limiting function, omega infinity. And the convergence is happening uniformly over every compact subset of R. So in some sense, I have a sequence of growing diagram. And if they are growing and growing, but if you rescale, you approach some limiting shape. OK, so the first question is the following. Take the limiting function, and it's going to describe you a domain, right, that is between this v line and the limiting function that you get omega infinity. So you pick x and y in this region. And then the question is, can you compute the limit as n tends to infinity of the value of t lambda at x, y, where you have to rescale everything in the good way? I will comment in a second. And t lambda T lambda n is a uniform random Stangian tableau of shape lambda n. So let's focus 1 second on the rescaling. So, more or less, this should be the same scaling that you get for a square. A square, in order to have n boxes, is square root of n times square root of n. So you expect that the vertical and horizontal rescaling is a factor of order square root of n. This delta is to fix this parity, this annoying parity story. And the value, the maximal value is n. So it should not be very complicated to guess that the right rescaling here should be 1 over n. So in this regime, you expect that something interesting should happen. And with a bit of being a believer, you guess, OK, there should be a limiting surface, index what x and y, that lives in this domain. And the limiting surface should not be too bad. OK, let me call a potential answer to this question answer 1. OK. So here it's exactly the same question with the same, I just copied and pasted. And this, I will call it the surface point of view of the question. And then you have the analog that is the height point of view question. That is, can you compute the scaling limit or this analog limit for the height function? So let me do it formally. So age xm is the function that I defined before. So it's counting how many boxes take a value less than m along the x coordinate. And now you fix x and t. X is a real number, t is in between 0 and 1. And you want to compute this limit. Why is this the right rescaling? Again, horizontally, you expect the same rescaling here. And it's a one-to-one map in this direction. The maximal value that you expect here to be interest is n. So I'm fixing t between 0 and 1. So this should be t times n. And then along each vertical line, roughly you expect a square root of n boxes. And so here now the rescaling is by a factor square root of n. So again, after this rescaling, you expect to have a limiting height function that is, in some sense, should be interesting, should be not trivial. You can always say, OK, I want to add our regime, but the belief is that in any other regime, you get something that is either trivial or no sense that is exploding at plus infinity. And I call an answer to this question 2, answer 2. OK, remember our relation that is saying if I give you the height function, you can recover the tableau. This is true at the discrete level. And you expect that the same relation, if the limits are not too bad, it's true at the continuum level. So almost, in the sense that the relation is true, but what you can prove is that if you have an answer to choose, so you know the height function, you can recover the surface under the assumption that the surface is continuous. The limiting surface, the limiting Young tableau in the surface point of view is continuous. If you have these, then the two problems are exactly equivalent. And it's not too hard to prove. The other thing that you have to be a bit careful is that we are taking random limits, right? So we have to be a bit more. But this is not too hard to prove. OK, what is known about this question? So the first result that I know is by Philippe Bihan in 2001 that shows that the limiting surface is infinity always exists under the assumption that I made before, that is that the limiting profile approach something after the rescaling. And his techniques are mainly coming from what is called free probability theory. So I'm honest, I'm not at all familiar with these techniques. But together with my co-authors, we try to investigate a bit with people that are familiar. And actually, Bihan is the advisor of Valentin, that is one of the authors. And it seems very, very hard to get out some explicit description of the surface from these existence results. In the sense, you can prove that it exists, but then if I ask you, can you compute it? Or can you say something? It's too implicit. there are a lot of cumulance computation that don't seem very, very tractable. So motivated by this fact that was known by several people, Romick and Pittel try to solve the case where you fix the diagram to always have square shape or rectangular shape. So it's either a square, fixed, or rectangle. And they explicitly computed both age, that is the age that you were asking, and T, that is the surface, in the rectangular case. And their techniques are mainly using the fact that you can count. So this Hooke formula and a lot of other counting arguments. I'm not saying that it's a trivial proof. It's a very smart proof. It's a very elegant proof. I really love it. But it has this limitation that you really need to access very explicit computations. And in their paper, they claim that it seems to be untractable to do a bit more than rectangular. Already rectangular was quite enough. And finally, there is a paper of Sun, which is a PhD student of Cédric, where he proved the existence of the limiting height function and the limiting surface in even a more general case that is the skew shape. In some sense, you don't ask that only the top approaches things and the bottom is always a V. You are allowed to let also the bottom part to take weird shapes, and you don't restrict to the fact that it's a V.
These are all results for uniform measure?
Yeah. Fix the shape, assume that the shape has a scaling limit, take a uniform at every scale, and what is the limiting surface. And the technique of Sun are very different from the previous two, and are mainly based on a variational problem. So he's able to say, okay, there is a limit, and the limit is the unique solution to this variational problem that is saying you need to find the surface that is maximizing some surface tension, and the surface tension is completely explicit. Problem one is that solving this variational problem is not clear that you can do it. Problem two, there is a problem in the proof, in the sense that we discovered that actually there is a small tricky technical problem in the proof, but that will have a very important gap in the word result, in the sense that when you go from age to T, it's actually false. And we will see later why. Okay, any question about that? Okay, let me tell you what are our main results. So first of all, we are not working in this general shape assumption where the previous results were stated. We're going to make an additional assumption that is the following. We look at what is called the multi-rectangular setting case. So what you do is the following. You fix lambda 0, a given diagram that you like. Can be as complicated as you want. Okay? But it has to be a Young diagram. Okay? A Young diagram. Okay? But you can take as complicated as you want. But once you pick up the shape that you like, it's fixed. And it has to be a Young diagram type of shape. Now, what you do, you call this the reference diagram lambda 0. And what you do is, for every little n, you replace in each box the box by an n by n grid of boxes. And so in this way, you go from lambda 0 to lambda capital N, where capital N is what? Is the size of what you get. I got trapped. Is the size of what you get. That is, you have lambda 0 boxes times n squared for each box. So capital N is, yeah. OK. So capital N is the size of the diagram that you get after doing this operation. So in some sense, if you increase little n, you increase capital N, and you're making this mesh finer and finer. OK, so I need a bit of notation. So remember, lambda 0 is fixed. So the white shape will never move. So look at the profile. You have some local minima and some local maxima, and actually they always alternate, right? So I will denote the position of the local minima by AI for A0, the first one, and AM, the last one. And BI is the position of the local maxima of the profile. So these are called in the literature the interlacing coordinates of lambda 0. Why interlacing? Because AI and BI, they always alternate. There is always one more A than B. So A will start from 0 and B will start from 1. Last operation that I do is the following. I do a little rescaling to lambda 0, but this is not needed. It's just to make the formula later on a bit nicer. So I pick eta to be just 1 over square root of the size of lambda 0. Okay, so it's a number. 1 over square root of the size of lambda 0. And I rescale x and y coordinates by this lambda. Okay, so I'm just rescaling a bit this shape y. Now the total area inside the lambda 0 after this rescaling is always 2. So whatever you choose at the beginning, after picking this eta and doing the rescaling, you have that the total area is 2. And having this fixed total area make the formulas always the same. So that's why. So again, I'm just rescaling here and here by lambda. By eta, sorry. Okay.
Total area is 1.
It's 2 because, again, it's, you have integer inside. So this is,
Okay.
right?
Squared.
Yeah. This is 0 and this is 2. Every box has size 2 at the beginning. But again, you can make it 1 if you like it, but we will just change the formula later on. And finally, since now this limiting shape lambda 0 is fixed and we will just replace this one, obviously this is our omega infinity. We'll never move this red function, right? This is the assumption in some sense, that we have this fixed limiting profile that is Young diagram type and is not any function that you like. Okay, the result that we have is the following very explicit formula for H infinity. Okay, let me walk you through what is saying this formula. So first of all, it's 1 over pi. I think all of you are good with that. And it's an integral from 0 to t in ds of 1 over 1 minus s, all good. And then there is the imaginary part of some function. And now I'm going to tell you what is this function. How do you get this function? In the following way. So look at here. You have lambda 0 fixed. Given lambda 0, you can compute eta, ai, and bi, these interlacing coordinate. And then you cook up this equation. It's a polynomial equation in the variable u, which is a complex variable. Pretty simple polynomial. It will depend on this eta, on this bi, ai, and on 2 additional parameters that are x and s. Okay? So now you have a polynomial equation. And UCXS is the unique complex solution to this polynomial equation, which is in the upper half plane. Okay. First of all, there is a very tiny lemma which was copied and pasted from a paper of Petrov. But it's really a very basic lemma that is telling you that actually, this is a polynomial of degree m plus 1. It's going to tell you m minus 1 solution of this polynomial are always real. So at most, you have 2 complex solutions. One is the conjugate of the other. When you have this complex solution, take UC to be the complex solution in the upper half plane. If there isn't, there are cases where everything is real. Just take UC to be 0. And then once you have this complex solution, this numerator is just the imaginary part of this number. And this makes computation incredibly explicit because you fix the polynomial that you want. This is a polynomial equation. You plug in a computer. It's easy to solve. You see, and then you compute this integral. Everything can be done in a really fast way. And we have many examples in our paper where you can make very explicit computation with this procedure. So for people that are familiar with Los tilings, this is something that is really, really related to that, and I will comment on that later on. So last comment, this equation in the statistical mechanics literature is called the critical equation, and we will keep this terminology, and I will explain at the end of my talk why it's called the critical equation. Yeah?
The way that you prove that there is at most one pair of non-real solutions is by constructing solutions in certain intervals between A's and B's or something?
Yeah, it's you look at where the polynomial is changing sign, and you force at least m minus 1. And then you don't know where they are the other two, and the other two you don't know where they are because it's really something that depends on where you put x and s. But yeah, it's a very basic lemma. There is nothing deep to do. I think any in this room can solve it. Okay, question about this statement? Yeah.
What is C? Does it stand for something?
It's just the U critical. It's just to mark it in but yeah, it's because it's the solution of the critical solution. Yeah.
Is there any obvious or reasonable intuition for why UC is equal to 0 in the right places?
I will comment on that later on. Yeah, that's a good question. Any other question? If it looks mysterious, it must be mysterious. I didn't explain where everything is coming from. You need just to understand what is the statement. So let me write it down here in such a way that we have it. So I use P. Yeah, P. Okay, this is the formula that we got.
Is it easy to say what U is with, say, the Patel-Roman?
No.
It's not.
In the sense, we didn't find immediately exact connection between our formula and their formula.
But their formula is like for a rectangle, right?
Their formula is for a rectangle, and we cover the rectangular.
That's what I'm asking. What is it in the situation of a rectangle? Is it easier or?
We recover exactly their formula, and it's very, very easy. It's super easy. We have a.
So
if you open the. Huh?
M equals 1 for the rectangle.
Yeah.
So it's a quadratic equation.
Yeah.
That's what I'm asking.
We solve it explicitly in the paper. It's one of the examples that we gave explicit for. Yeah. Okay, the second theorem, which is maybe less expected for people that are familiar, is the following. That actually we prove that this limiting surface, the infinity, is continuous in the whole domain only if and only if the interlacing constant, the interlacing coordinate have a very, very specific structure. They need to solve this system of equations. You have m minus 1 equations. You really need to tune the shape in such a way that AI and BI, they solve this thing. As soon as you're out from this regime, the surface has at least one discontinuity point. So the moral is, for almost every shape, if you take a general shape, there is probability 1 that the surface will be discontinuous. Apart one case, that is the rectangular case. Because in the rectangular case, m is 1, so you have no equation, so the surface is always continuous. Okay, I go in order.
So is this where the gap was in the previous work?
Exactly. In the previous work, they were assuming that the limiting surface is continuous to pass from one to the other, but it's almost never continuous. So this is a tiny gap that is for almost every case.
The h function is continuous, right?
The h function is continuous. It's 2 Lipschitz, actually. Square root of 2 Lipschitz, maybe. Any other question?
Oh, you already answered. That's what I wanted to ask.
And it's really only the rectangle.
And in the rectangular case, whatever rectangle you take, it's going to be continuous.
Right.
But as soon as you add one more valley,
You're going to violate.
you're going to violate always this, apart if you tune the valley in a very, very specific way. Okay, other question about the statement that they look.
Will you show us what magically is happening when these identities are true?
Yeah.
At this point, it's more.
I'm going to explain exactly where we get this. This is the next part of the talk. Next part of the talk, first I will explain this, and then I will explain theorem 1.
So in the context of sun, when they have for skew shapes, there cannot be also discontinuities also on the other.
Yeah. You will see that you get exactly everything also on the bottom part. Other questions?
For this Sun's paper, can you just restate it in terms of this other height function? And will that paper then work?
Say it again, sorry.
He was saying that in the paper of Sun, if you just restate it in terms of the height function, will everything work there?
No, the height function part, I guess it's okay. There are no holes. Even if, as far as I know, this paper is not published after 5 years. So I don't know if someone found any other problem. Or Sun, I think, left academia, maybe gave up. I have no idea. But at least from the variational problem, he gets the Borga equation for age, and we get exactly the same Borga equation. So at least there shouldn't be big mistake in the statement. Then in the proof, I don't know. It's a 90 pages paper, which is rather technical. Okay, so first of all, let's understand where this critical equation is coming from and what's going on. So before that, we need one more bijection. That is a very standard bijection. That is a bijection between tableau and bead configurations. So how do you do it? It's pretty easy. For every vertical line here, you have a vertical line correspond here that we will call a thread. So the 0 thread is corresponding to this. And in the x thread, you put a bead at height t if there is a box here with value t. So for example, in the 0 thread, you have a bead at height 1 and 5, because you have 1 and 5, here 2 and 8, this 2, and so on. So this is called a bead configuration, and it has the nice property that the beads are interlacing, in the sense that if you fix 2 consecutive beads on a thread, there is always exactly 1 bead between this value on the left and 1 bead between this value on the right. And this is true for every pair. So this is what is called a bead configuration, is these beads on threads. Okay, in infinite volume, you need to assume that the configuration are locally finite with this interlacing condition. And the height function now is a very obvious interpretation. If you want to compute, for example, age 17, you look just at height 7, and you count how many beads are below 7. Here it's 1. Here for x0 is 2. So age xt, just count how many beads are below t in the thread x. And theorem 1, for people that know this kind of thing, if you remove the integral, it's going to tell you this expression here is just the asymptotic density of beads that you see in the limit around xt. Nothing more. The height is just the integral of the density. Okay, here it's one example that I call the art example for obvious reason. So here, I have a tableau of this shape, and I took the easiest non-trivial example where A, B sequences do satisfy this critical equation. Okay, so here it's m equal to 2, so you have one equation, because you have m minus 1 equation. I take A, B sequences such that you have everything tuned up. And so you see that the limiting surface, here I think I have 10,000 boxes, something like that. It's a uniform one. You sample using this Hooke formula. It's an amazing proof of a formula that gives you an amazing algorithm to sample efficiently. And so you plot the limiting surface. Then you construct the corresponding Bead configuration, which is here. This is the corresponding height function. And what is this? This is what in the statistical mechanics is called the frozen region. Or inside this region is called the liquid region, outside the frozen region, and this is the boundary. Okay, what is this shape? Is exactly, can be defined as follow, is the shape where in the limit, if you go inside, you see a positive proportion of beads around every point in the interior of this shape. So our techniques will give an exact formula for the parameterization of the boundary. So you can write down an explicit formula for this liquid region, and you can compute everything.
The three-dimensional plot is the H function or the T function?
This is H function. This is T function. This is Bead model. Okay, so I want to stress something. You see that there are regions where there are no beads. Okay? And again, this is the parameterization of the domain where you see in the limit a positive proportion of beads. Okay, here is a second example that is a pipe example. Again, I think for obvious region. Okay, what's going on here? I took a very weird Young diagram, lambda 0. This is fixed. And it's done like that. You have a big bulk of the diagram, and then you have a very thin part of the diagram that is going like that. You should imagine that this is 100, 199, 100 again. And then you have this very thin 100 by 1 boxes that I put it there. So I will tell you why I did this, but here you don't satisfy at all this equation. You're very off from the equation. Then you do simulation, you look at the picture and you say, okay, yeah, it's true that it's very different, the shape, but if you do it from the previous picture, you don't see anything really different. If you look at the surface, here I zoom a bit, and from a long time, obviously, this is not my first simulation. When I tried, I took reasonable shapes. And I was keeping getting continuous surfaces. And I was like, where I'm wrong? The point is that this is not continuous. But it's incredibly subtle story. So if you look, this is the domain. And if you zoom inside this point here, what happens is that you can find a point here that is a bit in the continuation of this part of the domain inside here, where if you go up along this vertical line, the surface is like tiny splitting in the sense this part should be really continuous, but you see that there is a jump. But to get there, I had to skew the things like crazily and really go up to, I think, 1 million boxes. Otherwise, really, from simulation, it's so hard to see this discontinuity phenomenon. And I tried really a lot of shapes. This is the best one that I got, and it's still. So this is when I really like maths, in the sense where something is almost obvious mathematically, and we will see it. But if you do simulation, it's not so obvious that you get this kind of discontinuity. Okay, but the question is, what's going on? What's the issue? The problem is in this shape. So remember that this shape here is just telling you where there is a positive density of beads in this shape there. Okay, what's going on? That if you look at this picture, there is an issue. There is an issue when you fix a vertical ray at position x, where x is tuned in the following way. I chose x in such a way that the vertical thread here has the following property. You are out of the region, inside the region, out of the region, inside the region, out of the region. So there is a tiny thing here where you go out of the region. What happens? That here there is a non-empty interval that is out of the region. And so this means that our height function, if you look at the vertical direction, has a sort of plateau at a certain point. So it's flat, it's going up, then flat again, then going up, and then flat again. But remember that the construction was saying the flat part is telling you how much up you have to go in the surface. So if you have a non-empty flat part in the middle, it's telling you that you have a jump in the surface, which is exactly the definition of discontinuity of the surface. So whenever we are allowed to do something like that, the limiting surface will be discontinuous. The problem is that, you see, for some weird motivation, the shape that you get are never really permitting to choose this thing in a very macroscopic way. It's always this tiny mistake that you do. But it's very easily mathematically to know when this is possible or not. What you do is the following. You look at this cusp. You compute the tangent of the cusp, and it's the same from left and to right. It's pretty easy to show. Think about, I don't know, y squared equal to x cubed. And what you want to know is that as soon as this vertical tangent is not, this tangent is not exactly vertical, it's a bit non-vertical, you have a non-empty area where you can go out. So in some sense, the critical equation, theorem 2, is exactly the unique criteria that is telling you if you have this parameter, all the tangents at the cusp point, and you will have m-1 cusps. You need that all of them are vertical. Okay, so this is the thing is, we have an explicit parameterization of these in the general case. You compute all the tangent at all the cusp point, and you impose that the tangent is vertical. And coming back to the comment before, you have cusp point also in the bottom part, and you need vertically again. But our techniques are not going up to the skew case, and I will tell you why in a second. OK, what about theorem 1? I will have to skip most of it, because we have 5 minutes to the end. But let me give you the 2 main tools, at least. The first tool is something that is rather standard in the literature. Is instead of looking at a uniform standard Gantt tableau, you look at the Poissonized version, which means I fill boxes by real number between 0 and 1 in such a way that I have exactly the same monotonicity constraints when I go upwards. And I take uniformly at random one such configuration. You have to make sense of this, but roughly speaking, the valid configuration are a subset of 0, 1 to the n, the interval 0, 1 to the n, under some constraints that are, the constraints are you want to respect this monotonicity. And you can show that the subset that satisfies this constraint is a set with a non-empty interior, bounded, because it's inside this box. And so you have a good notion of Lebesgue measure in this set, and you pick one according to the Lebesgue measure, rescaled by the volume, and it becomes a probability measure. And then you construct m lambda exactly in the same way, with the only difference that now we go from 0 to 1. Okay, this is the first idea. And the big tool that we use is a result of Gorin and Rahman that is telling you that m lambda, that is, again, the Bead process constructed from the Poissonized version, is a determinantal point process. So it's a determinantal point process with a very explicit kernel, which rewrites as the double integral over 2 contours of some explicit function. Not the nicest function ever, but it's explicit. And OK, and these contours, they have a certain number of properties. One is inside the other, depending where T1 is. And then you have to contain certain specific interval for the 2 contours. And the only thing that you need, why you need to contain this interval is because the poles of this function are exactly in these 2 intervals. And then you want to keep the contour far enough in such a way that this thing is not exploding. So the poles are all in this green interval, or in this, for probably W, for Z are all here, and then there is an additional pole coming from Z equal to W. So I will, the whole theorem 1 reduces to the following question. How do you compute an asymptotic for this kernel? And this is rather classical. The idea is to use what is called the steepest descent analysis. I always call it saddle point analysis, but I think it's more common to call it like that in this side of the world. The saddle point analysis is very classical for one-dimensional integral. For two-dimensional integral, I don't know exactly where it's coming from. I learned it from a paper of Petrov again. But I think he's citing the paper of Okunkov, and I don't know if Okunkov is citing someone else. But I asked around, and Okunkov should be the first one, right?
To apply this to random.
Okay, Cedric confirmed that should be the first one. So.
But the method itself, there are some books from 100 years ago.
Okay, saddle point analysis. Wikipedia is saying that it's something that Riemann knew. So okay. I'm not surprised if there was someone somewhere that used this idea. But the idea is very smart. I really love it. In some sense, I go fast because I have no time, but you can rewrite the kernel like that. Exponential of something times something that is nice. Forget about all the rest. It's exponential of something times something that is nice. And you want to keep this thing in such a way that is always negative when integrate. If this is negative, then everything is going to 0. What you do is the following. You do a very fine analysis of where these things are big, where these things are small. And you have your starting integration contour. And the very smart thing is that you move the contours in such a way that you are sure that now this remains negative. And in doing that, you can do it in a very, very efficient way. In some sense, you can move the contours in such a way that you never hit any of the poles, so everything is nice. And you pick up one only singularity that is, if you see here, white is purple is external and green is internal. Here we swap them. And in order to swap, you pick the pole zeta equal to W. And then all the rest of the proof is just do residue theorem. You do the residue, you compute explicitly the residue, and you get exactly this thing without the integral. And then in order to get the height function, you integrate this. OK, sorry for going fast. I'll be happy to explain whenever you want during the week. Final slide. So we also know how to prove local limits in the bulk. And the local limit is a new infinite measure on standard Young tableau. Is none of the measures that are typically studied, like Plancherel or something like that. It's coming from this infinite Bead process. We believe that if you push a bit more the analysis, you should be able to prove at least Tracy-Widom fluctuation for the first line. In the sense, if you fix a box in the first line, it should be Tracy-Widom. And then one natural question would be, what if you go out of this integrable world where it's no multi-rectangular, so you don't have this determinantal point process? This is very open, but I talked to Yves Stanpros, and he might have something. I can discuss if you want what he told me, but he might be able to say at least when the surface is continuing in the general setting. OK, thank you very much.